In the Amazon, one of the most dangerous mistakes is not getting too close. It is thinking you know what you're looking at. Some species survive because they hide well. Others survive because they look harmless, familiar, or easy to dismiss. And the worst ones are not always the biggest or loudest. Sometimes the real killer is the animal people mistake for a weaker cousin, a harmless copy, or just another piece of the forest. This episode is about the Amazon's most misidentified venomous and toxic threats. The species people read wrong, the warning signs they miss, and the fatal gap between what an animal is and what people assume it is. The forest changes character as the ground begins to hold more water. The leaf litter thins, replaced by a slick mosaic of moss, shallow puddles, and the exposed roots of trees that have learned to anchor themselves in soil that never fully dries. Humidity thickens the air until every breath feels slightly weighted, and light shifts from fractured gold to a softer, diffused glow filtered through layers of overlapping leaves. Sound carries differently here. Instead of the brittle crackle of dry debris underfoot, there is a damp quiet punctuated by distant drips, the low hum of insects, and occasionally a sharp, almost metallic chirp that seems too precise to belong to something so small. On the broad surface of a low leaf, suspended just above a thin film of water, a fragment of color appears that does not belong to any known palette of decay. It is too clean, too deliberate, too intensely saturated to be mistaken for anything organic in the usual sense. A small frog, no larger than the last joint of a human thumb, sits motionless at first glance. Its skin carries a luminous blue that borders on electric, broken by irregular black patterning that sharpens its outline rather than concealing it. In another part of the forest, the same body plan might be painted in yellow, so bright it almost glows, or in a deep crimson that seems borrowed from warning signs rather than living tissue. These are poison dart frogs, most famously represented by species within the genus Dendrobates, and they embody a completely different kind of visual strategy from the coral snake that moves unseen through shadow and ambiguity. Nothing about this animal is attempting to hide. Its posture is open. Its colors are placed in ways that enhance visibility rather than disrupt it, and its movements, when they occur, are short, deliberate, and unhurried. It does not dart away at the first disturbance, nor does it flatten itself into the substrate in an attempt to disappear. Instead, it occupies space as if it expects to be seen, and in doing so, it creates a moment of cognitive dissonance for any observer unfamiliar with the rules of this environment. Brightness, in most contexts, is associated with decoration, with harmlessness, with the kinds of signals that attract attention without consequence. In the Amazon, that association can be catastrophically wrong. The colors are not arbitrary. They are the product of a biological phenomenon known as aposematism, a signaling system in which an organism advertises its own defenses to potential predators. In the case of poison dart frogs, the defense lies not in teeth or speed, but in chemistry embedded directly in the skin. The surface that reflects such intense color is also saturated with alkaloid toxins, complex molecules derived not from the frog's own metabolism, but from its diet. Small arthropods, particularly ants and mites, contain precursors that the frog sequesters and transforms, storing them in specialized skin glands. Over time, the accumulation of these compounds turns the frog's body into a chemical barrier, one that does not need to be delivered through a bite or sting. Contact alone can be enough to produce a reaction. The relationship between diet and toxicity introduces a layer of ecological dependence that is often overlooked. In captivity, where these frogs are removed from their natural prey base, they gradually lose their toxicity because the specific alkaloids are no longer available to them. This means that their vivid coloration persists even when the chemical defense weakens, a reminder that the signal and the substance it represents are linked through environmental context. In the wild, however, the system is intact. The frog's brightness is a reliable indicator of its chemical arsenal, and predators that learn this association quickly adjust their behavior. Learning, in this case, is not theoretical. It is often reinforced through direct experience. A bird that snaps up a brightly colored frog and receives a mouthful of bitter, irritating compounds may immediately release it, shaking its head, wiping its beak, and associating that visual pattern with a negative outcome. Mammals that attempt to ingest such prey can experience more severe reactions depending on the species and the level of toxicity involved. In some of the most potent species, such as Philobates terribilis, the alkaloids include batrachotoxins that interfere with sodium channels in nerve and muscle cells, effectively locking them in an open state and disrupting normal electrical signaling. This can lead to paralysis and cardiac failure in sufficiently high doses, although such extreme outcomes are rare in natural predator-prey interactions where exposure is often limited. Despite this, the frog does not rely on delivering a lethal dose to survive. Its strategy is built around avoidance. The goal is not to defeat a predator in a direct confrontation, but to create a reputation that discourages the attempt altogether. Over time, predators in the ecosystem learn to recognize the signal and bypass the frog entirely, conserving energy and avoiding risk. This creates a stable dynamic in which the frog's visibility becomes its protection, and its survival depends on being noticed rather than overlooked. For humans, however, the interpretation of that signal is filtered through a very different set of expectations. Bright colors are often associated with artificial objects, with toys, with decorations designed to attract attention without consequence. When that association is carried into the rainforest, it creates a subtle but dangerous bias. The frog's size reinforces this misreading. It is small, delicate in appearance, lacking any obvious structures that suggest threat. There are no fangs, no visible stingers, no aggressive displays. Its skin appears smooth, almost glossy, reflecting light in a way that can make it seem more like a crafted object than a living organism. This perception can lead to a specific kind of mistake, the assumption that something so visually appealing must also be safe to handle. In reality, direct contact with highly toxic species can allow alkaloids to pass through cuts or mucous membranes, and even less toxic species can produce irritation if handled carelessly. Indigenous knowledge systems in the Amazon have long recognized these properties, using secretions from certain species to coat blow darts for hunting. The process is careful and deliberate, reflecting an understanding that the frog's defense is potent but not indiscriminate. It requires respect and precision, not casual interaction. Within the broader ecosystem, the frog's coloration also influences relationships beyond direct predation. Some species exhibit remarkable parental behaviors, transporting tadpoles on their backs to small water-filled cavities in bromeliads or tree holes, where they develop in isolated pools. In these elevated nurseries, the bright coloration of the adult can serve as a visual anchor in the complex vertical structure of the forest, allowing individuals to relocate specific sites among countless similar-looking plants. The same colors that warn predators may also facilitate communication and navigation within the species, linking survival strategies across different stages of life. Thermoregulation adds another layer to this interaction with light and color. Unlike larger reptiles that can bask openly to raise their body temperature, small amphibians are constrained by their need to maintain moisture. The thin, permeable skin that allows for gas exchange also makes them vulnerable to desiccation. As a result, poison dart frogs operate within narrow environmental windows using microhabitats, shaded leaves, damp moss, the undersides of vegetation, to balance temperature and hydration. Their activity patterns are tied to these conditions, and their visibility within these spaces ensures that the aposematic signal remains effective even in low-light environments. There is an understated complexity in how these frogs move through their world. Each short hop is calculated, not in the sense of conscious planning, but as the outcome of evolved behaviors that balance exposure and safety. They do not rush because speed is not their primary defense. Instead, they rely on the assumption that being seen is enough. This creates a rhythm that feels almost deliberate, as if the frog is participating in a system where clarity is more valuable than concealment. Yet, this clarity is only effective for those who understand it. For an observer who carries different assumptions into the forest, the signal can be misinterpreted or dismissed entirely. The brightness that should trigger caution instead triggers curiosity. The small size that should prompt careful observation instead invites approach. And in that gap between signal and interpretation lies the same fundamental risk introduced by the coral snake, expressed in an entirely different form. The Amazon does not adhere to a single visual language. It presents multiple overlapping systems of communication, each shaped by different evolutionary pressures and ecological roles. The coral snake uses contrast and pattern to create ambiguity among similar forms, forcing observers to question what they see. The poison dart frog does the opposite. It removes ambiguity as much as possible, presenting a signal that is meant to be unmistakable. And yet, both systems can fail when the observer applies the wrong framework to interpret them. As the frog shifts position and the light catches its skin at a slightly different angle, the color intensifies, momentarily appearing almost unreal against the subdued greens and browns of the surrounding vegetation. It is a display that feels out of proportion to the size of the animal, as if the forest itself has allowed a fragment of something brighter to exist within it. That impression is not accidental. It is the result of a long evolutionary process that has refined not just the chemistry of the frog's defenses, but the visual language through which those defenses are communicated. The lesson embedded in that moment is direct, but it requires a willingness to discard familiar assumptions. Beauty in this environment is not an assurance of safety. It is often the opposite, a declaration that the organism has invested heavily in being noticed, because being noticed is what keeps it alive. To ignore that declaration, or to reinterpret it through a lens shaped by entirely different ecosystems, is to misunderstand the rules that govern survival here. And so the frog remains in place for a few seconds longer, fully visible, fully exposed, and entirely unbothered by the possibility of being seen. It does not need to retreat into shadow, because its defense is already active, written into every cell of its skin and every wavelength of light it reflects. When it finally moves, it does so without urgency, slipping into the layered vegetation with the same quiet confidence it displayed in the open. The color disappears, but the implication remains, hanging in the humid air with a clarity that is difficult to ignore. In the Amazon, the most dangerous mistake is not failing to see what is hidden, but failing to take seriously what is placed directly in front of you. The forest does not always end cleanly at the river's edge. In many places, it dissolves into a shifting boundary where water, mud, and vegetation compete for space, creating a transitional zone that is neither fully terrestrial nor fully aquatic. The ground softens underfoot, each step releasing a slow, wet suction as organic material breaks down into a dense, dark substrate. Roots arch outward like exposed scaffolding, stabilizing trees that grow at improbable angles, while shallow pools collect in depressions that never fully dry. The air here is heavier still, saturated not only with moisture, but with the constant presence of microbial activity, the quiet work of decomposition that defines this edge environment. It is within this boundary that the form appears, not emerging dramatically but already present, as if it had been part of the mud all along. The body is broad and low, pressed close to the ground, its outline irregular enough to merge with the surrounding textures of wet soil and decaying leaves. The skin is mottled in shades of brown and olive, broken by darker patches that mimic the visual noise of the environment. At first glance, it is easy to register the animal as inert, a lump of organic material rather than something actively engaged with its surroundings. This is the marine toad, often classified under Rhinella marina, and its entire presence challenges the expectation that danger must move, chase, or strike to be effective. The body does not suggest urgency. The limbs are short relative to the mass they support, the gait slow and deliberate when movement does occur. The head is broad, the eyes set high, and the mouth appears perpetually neutral, lacking the expressive cues that might signal alertness or aggression. This is not an animal that commands attention through speed or display. It does not rely on stealth in the way a predator does, nor does it advertise itself with the vivid signals of aposematic coloration seen in poison dart frogs. Instead, it occupies a different category altogether, one defined by apparent passivity. That impression is reinforced by its behavior. The toad remains motionless for extended periods, conserving energy and allowing its body to equilibrate with the surrounding environment. As an ectotherm, its physiological processes are tightly linked to external conditions, and the damp, shaded margins of the forest provide a stable thermal and hydric context in which it can operate efficiently. When it does move, it does so without haste, covering short distances with a series of measured hops that seem almost reluctant. There is no indication in these movements of a system built for rapid response or aggressive interaction. The misreading begins here, at the level of lifestyle rather than appearance. The brain, conditioned to associate threat with activity, interprets stillness as safety. A slow animal, one that does not pursue or evade with urgency, is categorized as low risk, something that can be approached or ignored without consequence. In many environments, this heuristic holds. In the Amazon, it fails in ways that are not immediately visible. The toad's primary defense is not mechanical, but chemical, embedded in specialized structures that are easy to overlook unless one knows where to look. Just behind the eyes, on either side of the head, are enlarged glands known as parotoid glands. They present as raised, elongated swellings, their texture slightly different from the surrounding skin, but not dramatically so. These glands are reservoirs for a complex mixture of toxins, including bufotoxins and related compounds that can have profound effects on the cardiovascular and nervous systems of potential predators. The mechanism of delivery is fundamentally different from the active systems seen in many other venomous animals. The toad does not need to bite or sting. When threatened, it can exude a milky secretion from these glands, a viscous fluid that coats the surface of the skin. In some cases, physical pressure, such as the bite of a predator, can cause the glands to release their contents more forcefully, directing the secretion toward the point of contact. The toxin does not need to be injected, it only needs to reach sensitive tissues, such as the mucous membranes of the mouth or eyes, to begin exerting its effects. For many predators, particularly mammals and reptiles, the interaction follows a predictable pattern. The toad is encountered, assessed quickly, and often seized based on the assumption that it represents an easy, low-risk meal. The initial contact may be unremarkable, the texture of the skin not immediately signaling the presence of a chemical defense. It is only after the secretion enters the mouth that the response begins. The compounds act rapidly, producing irritation, excessive salivation, and in more severe cases, neurological symptoms that can include disorientation and impaired motor control. The predator, confronted with an unexpected and unpleasant experience, releases the toad, often engaging in behaviors that attempt to clear the substance, rubbing the face against the ground, shaking the head, retreating from the area. This sequence illustrates a critical aspect of the toad's strategy. It does not prevent the initial mistake. Instead, it ensures that the mistake is corrected in a way that is memorable. The predator learns, through direct consequence, that this particular form, broad, slow, unassuming, is associated with a negative outcome. Over time, this learning can generalize, influencing future decisions and reducing the likelihood of repeated attacks. The toad's survival does not depend on avoiding contact entirely, but on making contact costly enough to discourage repetition. The chemical composition of the secretion is not static. It reflects both the toad's physiology and its interaction with the environment. Diet, habitat conditions, and individual variation can influence the concentration and balance of compounds within the glands. This variability adds another layer of unpredictability to the system, as the exact effect of exposure can differ between encounters. In some cases, particularly with smaller predators or those lacking prior experience, the consequences can be severe, even fatal. In others, the effect is primarily deterrent, sufficient to establish avoidance without causing lasting harm. Within the ecosystem, the toad's presence influences more than just direct predator-prey interactions. Its role as a generalist feeder allows it to consume a wide range of invertebrates, contributing to the regulation of insect populations in the transitional zones it inhabits. At the same time, its own vulnerability during early life stages, eggs and tadpoles, introduces it into a different set of relationships, where aquatic predators and environmental conditions shape survival rates. The chemical defenses that protect the adult are not fully developed in these earlier stages, creating a temporal window in which the species is subject to pressures that differ from those acting on mature individuals. Reproductive behavior further integrates the toad into the dynamics of this boundary environment. Breeding often occurs in shallow, still waters, where eggs are laid in long, gelatinous strings that drift just below the surface. These structures, like the adults themselves, carry toxins that can deter some predators, but they remain part of a complex food web where multiple species interact with varying degrees of tolerance and adaptation. The transition from aquatic larva to terrestrial adult marks a shift not only in habitat but in the expression of defensive chemistry as the developing toads accumulate and refine the compounds that will define their adult survival strategy. The skin, beyond its role in toxin secretion, is also central to the toad's interaction with its environment. Amphibian skin is permeable, allowing for gas exchange and the absorption of water directly from the surroundings. This permeability necessitates a constant balance between maintaining hydration and avoiding exposure to harmful substances. In the damp margins of the forest, this balance is easier to achieve, and the toad's preference for such environments reflects the physiological constraints under which it operates. The same surface that allows for essential exchanges also serves as the interface for chemical defense, a dual function that underscores the integration of form and function in this organism. For humans moving through this environment, the toad often registers only peripherally. It is seen, if at all, as a stationary object that does not demand immediate attention. The lack of movement, the absence of striking coloration, and the general familiarity of the amphibian form contribute to its dismissal as background life. This is a different kind of oversight from those encountered in earlier chapters. It is not driven by confusion between similar species, nor by the misinterpretation of a clear signal. It arises from a broader assumption about what constitutes a threat, an assumption that prioritizes speed, aggression, and visible weaponry over more subtle forms of defense. The consequence of this misreading is not always immediate or direct. Unlike the bite of a snake or the sting of an insect, the toad's defense often requires a specific kind of interaction, one that brings the toxin into contact with sensitive tissues. This might occur through handling, through the accidental transfer of secretions to the eyes or mouth, or through the actions of animals that engage more directly with the toad as potential prey. The risk is therefore situational, dependent on behavior as much as presence. Yet the underlying issue remains the same. The failure to recognize that the animal's apparent passivity is not an absence of defense, but a different expression of it. As the light shifts and the boundary between forest and water becomes less distinct, the toad remains where it is, its body absorbing and reflecting the conditions around it. It does not need to move to assert its place in the ecosystem. Its defense is constant, a chemical layer that exists regardless of activity. When it eventually does move, the motion is slow and unremarkable, a brief repositioning that carries it a short distance before it settles again into stillness. The lesson embedded in this encounter extends beyond the specifics of the species. It challenges the broader framework through which risk is assessed in complex environments. In the Amazon, danger is not confined to the fast, the large, or the overtly aggressive. It is distributed across a spectrum of forms and strategies, many of which operate without drawing attention to themselves. The marine toad represents a point on that spectrum where the absence of visible threat is itself the mechanism by which the organism is underestimated. In bringing the sequence of chapters to a close, the toad expands the concept of misidentification from a matter of visual error to one of conceptual limitation. It is not enough to recognize patterns or to distinguish between similar forms. One must also understand that entire categories, slow, soft, passive, can be fundamentally misleading in this environment. The Amazon does not conform to the expectations that shape perception elsewhere, and the organisms that thrive within it exploit those expectations with a precision that is both subtle and effective. What remains, after the toad has blended back into the margins of water and soil, is a recalibration of attention. The forest is no longer a collection of obvious threats and harmless background elements, but a continuous field where significance must be evaluated at multiple levels. The quiet, unmoving forms that once seemed irrelevant now carry the potential for consequence, not because they have changed, but because the framework used to interpret them has shifted. And in that shift lies the final understanding. In the Amazon, the most persistent danger is not what is hidden, nor what is brightly announced, but what is consistently misunderstood at the level of assumption itself. The tree looks unremarkable at first, one among thousands rising in vertical competition toward filtered light that never fully reaches the forest floor. Its bark is layered and irregular, ridged in long vertical seams where moisture collects and lichen establishes pale, powdery footholds. Thin films of algae soften the surface in patches, giving it a faint green haze that shifts depending on the angle of light. Ant trails move along predictable routes, slipping in and out of fissures in the bark, and small fragments of leaf debris cling where humidity keeps everything just damp enough to adhere. It is the kind of surface that invites contact without thought. A hand placed against it would not feel like an intrusion into a living system so much as a simple act of balance, something done automatically to stabilize movement in uneven terrain. But the surface is not as uniform as it appears. Along one section of the trunk, just above eye level, there is a subtle interruption in texture that only becomes visible when the light strikes from a shallow angle. The bark here seems slightly raised, not in a continuous ridge, but in a clustered series of small, irregular protrusions. They do not move, they do not reflect light in any unusual way. They sit embedded within the structure of the tree, blending into the surrounding pattern of decay and growth so effectively that the brain categorizes them as part of the bark itself. This is where the error begins. The protrusions are not bark. They are bodies, dozens of them, pressed together in a dense aggregation that follows the contour of the tree. Each individual belongs to a larval stage of a moth species, many of which fall under groups that include medically significant genera such as Lonomia. Their bodies are soft in the structural sense, lacking the hardened exoskeleton of adult insects, but that softness is deceptive. It is concealed beneath a forest of spines, each one fine, brittle, and loaded with chemical compounds that transform contact into a biological event. From a distance, the cluster reads as texture rather than life. The coloration is subdued: greens, browns, muted yellows, tones that align with the palette of the bark itself. In some species, the bodies are arranged in such tight formation that their individual outlines blur into a single surface, a continuous patch that mimics the irregularity of lichen or moss. This is not camouflage in the traditional sense of hiding a solitary form. It is a collective strategy where multiple bodies create a composite image that dissolves into the environment. The effect is amplified by stillness. These caterpillars do not move unless disturbed, and in remaining motionless, they avoid triggering the visual cues that would otherwise draw attention. The spines are the critical feature, though they are rarely perceived as such until it is too late. Each spine is connected to a gland that produces venom, and the structure is designed to break or penetrate upon contact. Unlike the deliberate delivery systems of snakes or spiders, where a bite is an active event, the caterpillar's defense is passive but highly effective. The animal does not need to respond to a threat. It simply needs to be touched. The pressure of skin against the spines causes them to lodge and release their contents, introducing toxins into the upper layers of tissue. The composition of these toxins varies across species, but in some of the most well-studied cases, such as those involving Lonomia obliqua, the effects extend far beyond localized irritation. The venom contains compounds that interfere with blood clotting, disrupting the balance of coagulation and leading to a condition where internal bleeding becomes a significant risk. This is not an immediate dramatic response in the way a predator's attack might be. It unfolds over time, beginning with pain and inflammation at the site of contact, then progressing into systemic effects that reflect a deeper interaction between the toxin and the body's regulatory systems. The danger, however, is not limited to the most extreme species. Many venomous caterpillars produce toxins that cause intense pain, dermatitis, and localized tissue reactions that can persist for hours or days. The sensation is often described as burning or stinging, a paradoxical response given the visual softness of the organism responsible. This mismatch between appearance and effect is central to the problem of identification. The brain, conditioned by experiences in other environments, associates fuzziness with harmlessness. Soft textures are categorized as low risk, something that can be touched, brushed aside, or ignored without consequence. In the Amazon, that association is unreliable. The aggregation behavior of these caterpillars further complicates the situation. By clustering together, they increase the density of spines within a given area, effectively amplifying the potential exposure from a single point of contact. A hand placed against what appears to be a patch of textured bark may, in reality, encounter dozens of individuals simultaneously. The cumulative effect of multiple spine contacts can significantly increase the amount of venom delivered, intensifying the physiological response. This is not an accidental arrangement. It reflects a survival strategy where collective presence enhances individual protection, creating a deterrent that is more effective than any single organism could achieve alone. Within the broader ecological context, these caterpillars occupy a transitional stage in the life cycle of moths, a period defined by rapid growth and high vulnerability. They feed on plant material, converting leaf tissue into biomass that will later support metamorphosis into adult form. This feeding behavior places them in constant interaction with the plant community, influencing patterns of herbivory and plant response. Some host plants may produce chemical defenses in reaction to sustained feeding, altering the composition of their tissues in ways that affect not only the caterpillars but also other herbivores that share the same resource. Predation pressure is intense during this stage, and the development of venomous spines is one of several strategies that caterpillars use to survive. Birds, reptiles, and small mammals all represent potential threats, and each has evolved different approaches to handling or avoiding toxic prey. Some bird species learn to recognize specific patterns or textures associated with venomous caterpillars, avoiding them entirely. Others may develop techniques to remove or bypass the spines, though this requires experience and carries risk. Insects, such as certain parasitic wasps, can circumvent the external defenses by targeting vulnerable points in the caterpillar's body, laying eggs that will develop internally. These interactions create a complex web of relationships where defense and counter-defense evolve in response to one another. The caterpillars themselves are not passive participants in this system. While their primary defense is embedded in their structure, their behavior reflects an awareness of exposure. Many species choose resting positions that align with the natural lines of the plant, positioning themselves along stems or veins where their bodies extend existing patterns rather than interrupting them. Some exhibit synchronized behavior within clusters, maintaining consistent spacing and orientation that enhances the illusion of a continuous surface. These subtle adjustments contribute to the overall effectiveness of their concealment, not by hiding entirely, but by blending into categories that the observer does not question. Thermal regulation also plays a role in their placement and activity. As ectothermic organisms, caterpillars rely on environmental heat to drive metabolic processes. The surfaces they choose, sunlit bark, shaded leaves, areas with specific moisture levels affect their ability to maintain optimal conditions for growth. Clustering can influence this as well, creating microenvironments where heat retention or moisture conservation is enhanced by the presence of multiple bodies. These physical considerations intersect with their defensive strategies, as the same locations that provide favorable conditions for development may also increase the likelihood of contact with larger animals moving through the environment. The human interaction with these organisms often occurs in the most ordinary contexts. A person navigating dense vegetation, reaching out to steady themselves, brushing against a trunk to avoid slipping, or clearing a path through low branches may encounter these caterpillars without any prior indication of their presence. There is no movement to attract attention, no sound, no distinct visual cue that stands apart from the surrounding textures. The contact is immediate and unmediated, and the response is delayed just enough to obscure the source of the problem. Pain begins to develop, localized at first, then spreading, accompanied by redness and swelling that suggest an external irritant but do not immediately reveal the mechanism. This delay in recognition reinforces the initial misclassification. The brain, having already categorized the surface as inert, struggles to reconcile the emerging sensation with the earlier perception. By the time the connection is made, if it is made at all, the interaction has already occurred, and the consequences are unfolding. This is a fundamentally different kind of error from those described in earlier chapters. It is not a misreading of a visible signal, nor a failure to distinguish between similar forms. It is the absence of classification altogether, the decision to treat a part of the environment as non-biological when it is in fact densely alive. As the light shifts and the angle changes, the cluster of caterpillars becomes slightly more defined. Individual bodies can be distinguished, the spines catching faint highlights that reveal their density and orientation. The illusion of bark begins to break down under sustained observation, replaced by the recognition of a living aggregation that has successfully avoided detection until now. The realization is subtle but significant, altering the way the surface is perceived and, by extension, how it is approached. In the Amazon, the distinction between surface and organism is not always clear. Structures that appear static may be composed of multiple living components, each contributing to a composite form that serves both ecological and defensive functions. The venomous caterpillars exemplify this principle with a precision that challenges intuitive categorization. They do not rely on dramatic displays or obvious signals. Instead, they occupy a space where expectation itself becomes the vulnerability. The softness suggested by their appearance is not an invitation. It is a misdirection, one that leverages deeply ingrained assumptions about texture and threat. In an environment where those assumptions are unreliable, the cost of maintaining them becomes evident not through abstract reasoning, but through direct physical consequence. The tree remains as it was, layered, textured, seemingly inert, but the understanding of what constitutes that surface has shifted, revealing a complexity that demands a different kind of attention. And in that shift lies the core lesson. In the Amazon, the categories that feel most comfortable, soft, small, harmless, are often the ones least equipped to guide accurate judgment. Night does not fall cleanly in the Amazon. It builds itself in layers, beginning in the understory where light is already scarce, then thickening upward into the canopy until the entire forest shifts into a different operating state. The air cools slightly but remains heavy with moisture, and the sounds reorganize rather than diminish. Day-active birds fall silent, replaced by a dense acoustic field of insects, frogs, and distant movements that are more often inferred than seen. Visibility collapses into narrow pockets defined by whatever light remains. Moonlight filtered through leaves, faint bioluminescent flickers, or the controlled beam of a headlamp cutting through the darkness in a tight, artificial cone. Within that reduced field of vision, shapes simplify. Complex textures flatten into silhouettes, and the brain begins to categorize rapidly, often without full information. A large, dark form on the forest floor resolves into something with 8 legs and a low, spread body. For most observers, the classification happens almost instantly. A big spider. The label feels sufficient. It carries a vague sense of caution, perhaps a mild aversion, but rarely the kind of focused attention reserved for animals that are widely recognized as dangerous. In a forest where large arthropods are common, where tarantulas, whip spiders, and various other forms share overlapping space, the category itself becomes a mental shortcut, a way to compress complexity into something manageable. That shortcut is exactly where the problem begins. The animal in question belongs to the genus Phenutria, commonly referred to as the Brazilian wandering spider. Its presence on the forest floor is not incidental. Unlike web-building spiders that anchor themselves to a specific location, this species is an active hunter, moving through the environment in search of prey. The term wandering is not a casual descriptor, but a precise reflection of its ecological role. Each night, individuals leave their daytime refuges, crevices, leaf axils, under loose bark, and begin a controlled, deliberate patrol through the understory. Their movement is not erratic. It follows gradients of scent, vibration, and subtle environmental cues that indicate the presence of potential prey. This roaming behavior immediately separates it from the more familiar image of a large spider waiting in a fixed position. Tarantulas, for example, are also capable hunters, but they often rely on ambush strategies from burrows or sheltered positions, conserving energy and minimizing exposure. Their bodies are heavier, their movements more deliberate, and their defensive responses, while effective, are generally reactive rather than proactive. The wandering spider operates under a different set of constraints. It trades the security of a fixed location for the flexibility of constant movement, and in doing so, it encounters a wider range of stimuli, prey, competitors, and threats within a single night's activity. The morphology of the animal reflects this lifestyle in ways that are easy to overlook if one stops at the category of large spider. The legs are long and built for rapid, controlled movement across uneven surfaces, capable of navigating leaf litter, roots, and vertical structures with equal competence. The body is comparatively streamlined, lacking the dense, velvety covering of setae that gives many tarantulas their distinctly heavy appearance. Instead, the wandering spider presents a more functional profile, optimized for speed and responsiveness rather than bulk. Even the orientation of the legs, held slightly elevated and ready to adjust, suggests an organism that is constantly processing its surroundings rather than settling into a static posture. Sensory input plays a central role in how this spider interacts with its environment. Vision, while present, is not the primary channel. The forest floor at night does not provide the kind of consistent visual information required for long-range targeting. Instead, the spider relies heavily on mechanoreception, fine hairs and slit sensilla distributed across the legs and body that detect minute vibrations in the substrate and air. A struggling insect, the movement of a small vertebrate, even the subtle shift of air caused by something approaching, all register as patterns that can be interpreted and acted upon. This creates a form of awareness that is distributed across the entire body, allowing the spider to respond to stimuli that may never fully resolve into a clear visual image. When prey is detected, the response is immediate and precise. The spider closes distance quickly, using short bursts of speed rather than sustained pursuit, and delivers a bite that injects venom through relatively large chelicerae. The venom itself is a complex mixture of neurotoxic peptides, evolved to interfere with ion channels and disrupt normal nerve function in prey. In insects, this results in rapid immobilization, preventing escape and allowing the spider to subdue and consume the organism efficiently. In vertebrates, including mammals, the effects can be more complex, involving pain, muscular disruption, and systemic responses that vary depending on dose and point of contact. One of the defining features of the Brazilian wandering spider, however, is not its predatory behavior, but its defensive posture. When confronted with a perceived threat, the animal does not immediately retreat. Instead, it reorients its body, raises its front legs high off the ground, and exposes the ventral surface in a display that is both striking and informative. This posture increases the apparent size of the spider, elevates the chelicerae into a ready position, and presents contrasting coloration on the underside that may function as a warning signal. The movement is controlled, not frantic, and it communicates a clear shift from passive presence to active defense. This is a critical moment, and it is often misread. To someone operating under the broad category of large spider, the display may be interpreted as bluff or exaggerated threat, something that can be dismissed or avoided without consequence. In many cases, with other species, that assumption might hold. Numerous large spiders rely on intimidation as a primary defense, lacking the capacity to inflict serious harm on larger animals. The wandering spider does not fit that pattern. Its venom is medically significant, and while severe outcomes are relatively rare, the potential for intense pain and systemic effects is well documented. The defensive display is not empty. It is a clear signal that the animal is prepared to escalate if the threat continues. The confusion arises not because the wandering spider looks identical to harmless species, but because it fits into a mental grouping that is too broad to be useful. 8 legs, a certain size range, a general brown coloration. These features are shared by a wide array of arachnids in the Amazon, each with different behaviors, ecological roles, and levels of risk. By collapsing that diversity into a single category, the observer loses access to the specific information that would allow for accurate assessment. The brain, seeking efficiency, stops at recognition instead of continuing into differentiation. In ecological terms, this kind of grouping has consequences beyond human perception. Predators that encounter multiple spider species must also navigate this diversity, and their responses are shaped by experience and outcome. A predator that attempts to consume a wandering spider and experiences a negative reaction may generalize that experience to other similar-looking spiders, avoiding them in the future. This creates a form of indirect protection for species that share certain visual traits, even if they lack comparable defenses. At the same time, it reinforces the effectiveness of the wandering spider's strategy, as its reputation extends beyond direct encounters. The environment itself amplifies these dynamics. The forest floor at night is a space of limited visibility and high uncertainty, where decisions are made quickly and often with incomplete information. The cost of hesitation can be exposure to other threats, while the cost of misidentification can be immediate harm. Under these conditions, Both predators and humans rely more heavily on heuristics, mental shortcuts that simplify decision-making. The problem is not that these shortcuts exist, but that they are applied without sufficient resolution. Large spider becomes a stand-in for a range of possibilities, some trivial, others significant. The wandering spider exploits this gap not through deception, but through the absence of clear differentiation in the observer's mind. It does not mimic another species or hide its features. Instead, it exists within a category that is too coarse to capture its specific traits, allowing it to be underestimated by those who fail to look more closely. This is a different kind of misread from the coral snake's mimicry or the poison dart frog's misunderstood brightness. It is not about confusion between similar signals or misinterpretation of a clear warning. It is about the decision to stop processing information before the relevant details emerge. As the night deepens, the spider continues its movement, navigating the uneven terrain with a consistency that suggests familiarity with the microstructure of the forest floor. Each step is placed with precision, avoiding obstacles, adjusting to changes in texture, responding to signals that remain invisible to any observer relying solely on sight. When it encounters a potential shelter, a curled leaf, a hollow beneath a root, it pauses briefly, assessing the space before either entering or moving on. This constant evaluation reflects a balance between exposure and protection, between the need to hunt and the need to avoid becoming prey. Eventually, the animal disappears into one of these temporary refuges, its form dissolving back into the complexity of the environment. The forest returns to its layered sounds and shifting shadows, and the space it occupied becomes indistinguishable from the rest. What remains is not the image of the spider itself, but the realization that the initial classification, quick, efficient, and seemingly adequate, was never sufficient to capture the reality of what was present. In the Amazon, danger does not always announce itself through obvious extremes of size, color, or behavior. Sometimes it resides in the details that are easy to overlook, embedded within categories that feel familiar enough to discourage further inspection. The Brazilian wandering spider embodies this principle with a quiet precision. It is not hidden in the way a camouflaged animal is hidden, nor is it brightly advertised like a poison dart frog. It exists in the space between, where recognition is achieved just quickly enough to prevent deeper understanding. And in that space, the most costly mistake is not failing to see the animal at all, but believing that seeing it once under a broad, comfortable label is the same as truly understanding what it is. The forest floor looks calm in a way that is almost instructional, as if it is offering a lesson in how easily the human eye can be convinced that nothing urgent is happening. Leaf litter lies in layered shades of decay, bronze, black, and deep olive, each fragment softened by humidity and time. Thin roots stitch through the soil like exposed veins, and shafts of filtered light break through the canopy in narrow golden columns that illuminate only fragments of the ground at once. In that shifting mosaic of brightness and shadow, movement does not announce itself. It dissolves into the environment until it is nearly indistinguishable from it. And then, without any escalation or warning, a pattern resolves out of the stillness. A sequence of clean, repeating bands, red, black, yellow, sliding with deliberate calm across the forest floor. The animal is a coral snake, most commonly from the genus Micrurus, and it carries one of the most recognizable visual signals in the entire Amazon basin. The bands are not random decoration. They are a biological statement refined over millions of years, a signal shaped by the physics of light, filtering through foliage, by predator vision tuned to contrast and motion, and by the evolutionary arms race between those who hunt and those who survive by not being eaten. The colors are saturated in a way that seems almost out of place against the muted palette of the forest floor, but that contrast is precisely the point. In low, green-filtered light, bold, alternating bands remain legible at distances where subtle patterns disappear. To a predator scanning quickly, bird, mammal, or reptile, this is a high-visibility warning that cuts through visual noise. Yet the Amazon does not reward simple interpretation. The clarity of that signal has been exploited by other species that carry none of the coral snake's venom but benefit from its reputation. Across the same patch of forest, nearly identical banding patterns appear on harmless or only mildly defensive snakes, false coral snakes that belong to entirely different families. These mimics have evolved under intense selective pressure because any resemblance to a dangerous species increases the odds of being left alone. Over generations, predators that hesitate at the sight of red, black, and yellow inadvertently reinforce the survival of those imitations. The result is not a single reliable warning system, but a layered visual language filled with deliberate deception. Some species copy the exact sequence of colors. Others approximate it closely enough that, in poor lighting or from a distance, the difference collapses. This is where the idea of recognition begins to break down. In controlled environments, outside the complexity of the rainforest, people are often taught simple rules to distinguish dangerous coral snakes from their mimics. Color rhymes, sequence mnemonics, quick visual shortcuts designed to compress identification into something immediate and usable. But those rules are built on clarity that rarely exists in the Amazon. Light shifts constantly as the canopy moves. Moisture darkens colors and alters contrast. Dirt, algae, and abrasion interrupt clean banding. Juveniles may present patterns that differ from adults, and regional variation further complicates any attempt at universal identification. What looks like a clean sequence in a textbook becomes fragmented and ambiguous on a living, moving animal half covered in leaf litter. The coral snake itself does nothing to simplify the situation. Its body is slender, almost delicate, compared to the heavy, muscular forms of vipers that dominate the human imagination of danger. It does not coil into dramatic defensive postures or produce the kind of audible warnings that larger snakes use to advertise their presence. Instead, it moves with a quiet, controlled confidence, often partially concealed, relying as much on its coloration to manage interactions as on any overt display. This subtlety is part of its strategy. The snake does not need to escalate visibly because its primary defense is already built into its appearance. When threatened, some coral snakes will hide their heads and raise their tails, presenting a false target to confuse attackers. But even this behavior is restrained compared to the explosive theatrics of other venomous species. Beneath that understated exterior lies a venom system that operates on an entirely different principle from the heavy-bodied vipers that people tend to fear first. Coral snakes are elapids, closely related to cobras and mambas, and their venom is predominantly neurotoxic. Rather than causing immediate dramatic tissue destruction, it interferes with the communication between nerves and muscles. The molecules involved, alpha neurotoxins, bind to receptors at the neuromuscular junction, preventing signals from triggering contraction. In practical terms, this means that the body begins to lose control of its own movements. Muscles weaken, coordination fails, and in severe cases, the most critical system of all, breathing, can be compromised as the diaphragm and associated muscles stop responding effectively. What makes this particularly insidious is the potential delay between the bite and the onset of serious symptoms. A coral snake's fangs are relatively small and fixed at the front of the mouth, and envenomation often requires the snake to maintain contact, chewing slightly to deliver venom effectively. Because of this, some bites may initially seem minor or even inconsequential, especially if they occur quickly and without obvious immediate pain. This creates a dangerous psychological gap between cause and effect. The absence of immediate dramatic symptoms can reinforce the initial misreading of the animal as harmless or insignificant. By the time neurological signs begin to appear, slurred movement, drooping eyelids, difficulty breathing, the window for easy intervention may already be narrowing. The ecological context in which this interaction occurs only amplifies the problem. The Amazon is not a static environment where one can pause, analyze, and make careful decisions without consequence. It is a system of continuous demands: heat, humidity, insects, unstable footing, limited visibility, each one drawing cognitive resources away from careful observation. Under these conditions, the brain defaults to shortcuts. It categorizes quickly, often based on incomplete information, because hesitation itself carries risks. A snake that looks slender and non-threatening is more likely to be dismissed than one that presents a thick body and a triangular head, even though those visual cues are not reliable indicators of danger across all species. Predators within the ecosystem face similar constraints, and their interactions with coral snakes reveal how these pressures shape behavior over time. Birds that specialize in hunting reptiles may avoid brightly banded snakes altogether, even when some of those snakes are harmless. Mammalian predators, such as small carnivores, often rely on rapid visual assessment and prior experience to decide whether to engage or withdraw. A single negative encounter, an attempted bite that results in illness or impairment, can be enough to recalibrate future decisions, pushing the animal toward caution whenever it encounters similar patterns again. This learned avoidance benefits not only the coral snake, but also its mimics, reinforcing the entire system of shared visual signals. There is a quiet irony embedded in this arrangement. The coral snake's most powerful tool is not aggression or speed, but the ability to influence perception at a distance. Its coloration functions as a form of communication that extends beyond the moment of contact, shaping decisions before any physical interaction occurs. At the same time, that very signal has been diluted by imitation, creating a landscape in which certainty is difficult to achieve. The animal that is genuinely dangerous and the one that is merely pretending to be both occupy the same visual space, forcing any observer, human or otherwise, to operate under uncertainty. In this way, the coral snake becomes more than just a venomous reptile. It becomes a case study in how information is processed under pressure, and how errors in that process can carry real biological consequences. The danger does not begin with the bite itself, but with the initial interpretation of what is being seen. A wrong guess, made quickly, reinforced by incomplete rules, and executed in an environment that punishes hesitation, can set in motion a chain of events that unfolds long after the animal has disappeared back into the leaf litter. As the bands slip out of view and the forest returns to its apparent stillness, the lesson lingers in a way that is difficult to ignore. The Amazon does not always present its most serious threats in forms that match expectation. Sometimes the signal is bright, clean, and almost decorative, embedded in an animal that looks too small, too thin, or too composed to demand immediate respect. And in those moments, the greatest risk is not the venom waiting beneath the surface, but the quiet confidence of a mind that believes it has already understood what it is looking at.